Now we come to quantum mechanics. The pieces were now all in place for a new way to rationalize all these seemingly contradictory wave and particle behaviors of light and matter. One of the major driving forces behind physics has been the criticality of making accurate measurements of physical phenomena and then making predictions based on these measurements and see if those predictions can be measured correctly. This still holds for quantum physics, but there is a bit of a twist. There are times when the more accurate a measurement that you make of one quantity, the less accurate measurement you're going to make of another quantity that is complementary to it. This is expressed in the Heisenberg uncertainty principle, published by Walter Heisenberg in 1927. So here we are with the uncertainty principle. And the fact that this is in the x direction and this is the uncertainty in x where it is doesn't really matter. That could be the y direction, it could be the z direction, or in this case, which we're going to talk about here, it could be the radial direction, or r, if we're dealing with the circle. This actually explains why electrons remain in their orbits and do not spiral down to collapse in their nucleus. Niels Bohr had theorized that if an electron is in a quantized orbit, it does not radiate electromagnetic waves, so it does not lose energy. Well, that kind of violates what Maxwell came up with. Now let's look at Heisenberg's principle. Let's try and have that electron spiral down to the nucleus, get it real close. So in that case, delta R, that's the distance between the nucleus and the electron, gets very, very, very small. The uncertainty in that measurement is very tiny. We know that it's right next to the nucleus. However, if this is very small, delta x, then the momentum has to be very, very large. So if this electron gets really close to the atom, to the nucleus, then the momentum will be very large, its velocity will be very large, and that will prevent it from getting any closer to the nucleus. Here's another version of the uncertainty principle, which relates the uncertainty in the energy measurement and the uncertainty in the time at which the object is measured. Now, the nice thing about this is for physicists making measurements at levels that we can all see, the principle doesn't really come into play. For example, earlier we talked about a baseball. You can exactly know what its velocity, its mass, and its position is classically, because Planck's constant is so very tiny.